Properties of continuous functions. If the function f and g are continuous at some point on the x, we'll call that c, then the following combinations are continuous at x equals c. If I add my two continuous functions together, the result, or the sum, is also continuous. If I subtract my two continuous functions, then the result, or difference, is also continuous. And the same thing goes on and on. If I multiply my two continuous functions, the product of those two functions when multiplied is also continuous. Same thing with dividing. All right? If I have two continuous functions and I divide them, the quotient is also continuous. However, you need to remember that g of x in this case cannot be 0 because g is in the denominator. And if we have a 0 in the denominator, it is undefined. And there's one more here. This is the constant multiple rule. Right? If I have a function f and it's continuous, and I multiply it by some constant, okay, like let's say I multiply it by 7, or pi, or negative 13, and that continuous function, when multiplied by a constant, will still be continuous. Composite of continuous functions. If f is continuous at c, and g is continuous at c, or f of c, then the composite of the functions, g of f, is continuous at c. If you have two continuous functions, their composite is continuous. Point blank, quite simple. In case you forgot what a composite is, if I have two functions, the composition is taking one function and putting it into the other. In this case, I have to take g of x and put it into f of x. So I would have f of g of x, which would be, in my f, I now put g of x which means, instead of having x squared, I have x plus 3 squared. All right? That's just a quick review of composition of functions. I take one function and put it into the other function. Let's show that the following function is continuous. Y equals the absolute value of x times the sine of x all over x squared plus 2. Well, first of all, I'm going to look at this right here. This is a composition of two functions. All I got to do is break them down. Okay? So, I can see that I have the absolute value function here. So, one of my functions is going to be the absolute value of x. Okay? The other function is what gets put inside the absolute value. So my other function is going to be x times the sine of x over x squared plus 2. According to my rules, if I can prove that both of those functions separately are continuous, then the composite, or the combination of the both of those functions, is also continuous. First, let's start with this. This is just an absolute value. If I were to graph this, the absolute value function, when graphed, looks like this. That is definitely continuous. The absolute value is continuous. There you go. So this one, check, is continuous. So now I just need to check to see if my other fraction here is continuous. So, if my fraction is continuous, then my fraction is continuous when I put it into my absolute value, which is also continuous. Now, how do I figure out if that's continuous or not? I'm going to look back at all my sheets here. I actually have a fraction, right? So, my fraction can be continuous if my f and g are also continuous. So I'm going to look at them separately. If they're continuous separately, then the fraction is continuous. So, I need to prove that the numerator, x times sine of x, is continuous, and my denominator, x squared plus 2, is continuous. X squared plus 2 is easier. If I look at this graph, that's really a parabola that just moves up 2. And guess what? As long as there are no exceptions, parabolas are continuous. Check. So my denominator is continuous. I just need to make sure that my numerator is continuous. And guess what I have here? A product. Based on my rules, oh my lord, if both things I'm multiplying are continuous, then the product they create is also continuous. So, is x continuous? And is sine of x continuous? What is this here? X is just a straight line. Lines are continuous. So guess what? That's continuous. Sine of x. Sine of x is the trig curve that goes on forever like this. So guess what? It's continuous. Sine is continuous. If x and sine of x are continuous, then the numerator is continuous. If the numerator and denominator are continuous, this whole fraction is continuous. If the whole fraction is continuous, and we put it inside a continuous function, like absolute value bars, then the whole stinking thing is continuous. All right, let's do the same thing with this next example. Show that the following function is continuous. I am going to break this up into 2 separate functions. I have the square root function, my first one, and then I have what goes into the square root, second one. So I can say I have the square root of x is one function, and x over x plus 1 my next function. All right. Well, and I know that because if I were to combine these, I'd put this in for the x, and I would get the square root of x plus 1. First thing, I'm going to prove that they're both continuous. If they are both continuous, then the composition of them would be continuous. The square root function looks like this. Starts at 0 and goes like that. That is definitely continuous. The square root function is continuous. Check. Again, we have a fraction. If I can prove that the numerator is continuous and the denominator is continuous, then the whole fraction becomes continuous. All right? Well, that's just a 45-degree line. That's good. It's a line. That's continuous. This is the same line, just moving up 1. So that is also a line that is also continuous, which means bang, bang, which means the whole fraction is continuous. Now, my square root is continuous. My fraction here is continuous. Therefore, the composition of the two would be continuous. The intermediate value theorem for continuous functions. It states, if the f of x is continuous on some closed interval from a to b, then for any point on that interval, let's call it c, there is a value, which means f of c has some real number. It exists. Let's kind of take a look at this definition based on this graph we have below. Okay? It's saying if f of x is continuous, here's my graph of f of x. I'm just going to go over it. If it is continuous. Continuous means we can, in easy terms of understanding, we can draw that graph without lifting up our pencil once. It is a connected line. All right? And if f of x is continuous from some interval, let's call it from B to A. Here's value B on the x-axis. Here's value A. If you're confused with letters, you can say, okay, this is from 2 to 5. If you want to just make up numbers, okay? So f of x, our graph is continuous from 2 to 5. Or in this case, we're calling it A to B. Then there's some value C in that interval. Well, here's C. There has got to be some value between A and B. So in our case, between 2 and 5. I don't know, let's call this 4 maybe. Where there exists a value f of C, which means if I have an x value for 4, there has to be a y value. That just means there has to be a coordinate right there. There has to be something there. And that makes sense, doesn't it? If this is continuous from the beginning to the end, then I can pick any point in between here, and there'll be an actual coordinate. There's no hole, there's no asymptote, there's no jump, discontinuity. It is continuous. All right, is there any real number exactly 1 less than its cube? Compute any such value accurate to 3 decimal places. So let's create our equation first. Is there any real number that is exactly 1 less than its cube? So, how do we come up with that equation? Well, is there any number, let's call that number x, okay? Is there any number that is exactly 1 less than its cube? That means if I were to cube it and subtract 1, it would be equal. Okay? So all I'm going to do is get everything on one side set equal to 0 and solve. If I can. Alright? So, I'll subtract x from both sides. And if x 0 equals x cubed minus x minus 1. Alright? That would be a pain in the butt to factor. But we have graphing calculators and we can figure this out. So, they want to accurate to 3 decimal places. How am I going to do that? I'm going to graph it. And if I graph it, I should end up with this picture right here. And how do I know what the answer is to any polynomial set equal to 0? It's the x-intercept. It's where it crosses the x-axis. I want to figure out what this value is right here. So I'm going to put this equation back into the calculator and use my 0 function, my 0 calculation, to have the calculator give me what that value is. So, I'll go here, I'll clear this out. I have x cubed minus x minus 1. And when I graph this, let me make sure, 6 a standard window. That's what it looks like, okay? And I want to figure out, I'll zoom actually in, I want to figure out right where it crosses the x-axis there. So I'm going to go to second trace, this is my calculation menu, and I want to calculate the actual 0, which is choice 2. And for my students, I tell them I've got to make a bow tie. Notice the calculator's asking me for the left bound. See in the left bottom of the corner of the calculator screen, it says left bound with a question mark? It wants me to figure out what the left bound is. So I want my little spider dude moving just left of where it crosses the x-axis. And once I hit enter, it puts a little arrow there. Now it changes, it says, what's the right bound? So I've got to go just right of where it crosses. It doesn't have to be anywhere right. It could be here, could be here, it doesn't matter. And then I hit enter again, and it says, do you want me to guess? So yes, you do, so you hit enter one more time. But notice that the arrows are pointing to each other. It looks like a bow tie. You need to make a bow tie. If the arrows are pointing away from each other, you reverse your left and right side, and you'll get an error. So if your arrows are pointing to each other, you'll have to do it again. Hit enter one more time, and there's my answer. We'll put it right here. And they want it to how many decimal places? 3. So 3, 2, 4. My 4 will round up to a 5, because the number after it is 5 or bigger. 1.325 is an approximation for x, not exact. So we'll use this for units. All right, so now we've had some time to work on this one ourselves. Let's see if we've got it right. Is there any real number exactly 2 more than its cube? Compute any such value accurate to 3 decimal places. chapter? Well, let's start by creating an equation. Any number exactly 2 more than its cube, let my number be represented by x. Okay? Is there any number that is equal to 2 more than its cube? So I'm going to cube it and add 2. Now we're going to do the same thing we did for the previous problem. I'm going to bring my x over, set it equal to 0, and I'm going to use my calculator to do the brunt of the work. Right? So I'm going to subtract x from both sides. 0 equals x cubed minus x plus 2. That's what I'm going to graph. That's what I'm going to check to see where it crosses the x-axis. And where it crosses the x-axis will give me my solution. It is the x-intercept, it is the 0, it is the root, it is the answer. And look, there it is. So, let's put that in our calculator and see what we get. We go back to y equals, we have x cubed minus x, and the only thing that really changes is plus 2. So I'm going to make this plus 2. If I graph it, there it is. We kind of have the same thing here. We want to figure out where that line crosses the x-axis to find our x-intercept, our 0, our root, our solution. So again, I'm going to use a calc function in the calculator and hit second trace, because calc is above trace in blue. Pick my 0 function, and I'm going to make my bow tie. So I've got to go left. So where's this little spider thingy? There he is. Come on. Keep moving. Keep moving. Right now I'm above it, which is right. That will always be the case. It just happens it's the way this line slants. Okay? So left is below it. I hit enter. And I want my right, so I go above it, hit enter. Are those pointing toward each other? Absolutely. It's a cute little bow tie there. Calculator says, you want me to guess? Yes, that's why I'm doing it. And enter one more time. And there you go. So I'm going to take a look at this, put this here. And I'm going to round my answer to 3 decimal places, because that's what it's asking me for. 3 decimal places. That means the 1. It will stay a 1 because the number after the 1 is smaller than 5. So my x is approximately, because we are rounding, negative 1.521. There we go.